Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today's topic of discussion is engineering notation on the Texas Instruments TI-89 Titanium Edition Scientific Graphing Calculator, made in China. Trust me, if it was really from Texas, it'd be bigger and a lot more annoying. Our objective during this short lecture is to learn to enter and interpret engineering notation on the TI-89. This lecture operates under the presumption the user is marginally skilled at writing and reading numbers in proper engineering format, as illustrated in the engineering notation lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, only dimly recall its contents, please take the time to do so now. As you're no doubt aware, engineering format makes unusually large or unusually small numbers easier to write, read, and most importantly, conceptualize. The most commonly used range of engineering prefixes features the base unit, necessitating no prefix. The next largest prefix is the kilo, abbreviated small k, equivalent to 10 to the third or 1,000. The next larger prefix is the mega, abbreviated capital M, equivalent to 10 to the 6 or 1,000,000. The next larger prefix is the giga, abbreviated capital G, equivalent to 10 to the 9th or 1,000,000,000. Finally, the next larger prefix is the tera, abbreviated capital T, equivalent to 10 to the 12th or 1,000,000,000,000. These positive powers in steps of 3 are equivalent to leftward shifts of the decimal places from the base unit. For example, 13,500 volts could be more appropriately expressed as 13.5 kilovolts in proper engineering format. Returning to the base unit, one can also use engineering prefixes to represent unusually small numbers. The next smaller prefix is the milli, abbreviated small m, equivalent to 10 to the negative third or 0.001. Next smaller prefix is the micro, abbreviated as a funny looking U with a long tail, equivalent to 10 to the negative 6 or 0.000001. The next smaller prefix is the nano, abbreviated small n, equivalent to 10 to the negative 9th or 0.000000001. Finally, the next smaller prefix is the pico, abbreviated small p, equivalent to 10 to the negative 12th or 0.00000000001. These negative powers of 10 in steps of 3 are associated with rightward shifts of the decimal place from the base unit. For example, consider the ugly string of numbers 0.0002047 amps. This could be more appropriately expressed as 204.7 microamps in proper engineering format. This, by the way, should be a review of the aforementioned lecture. Today's task is to learn how scientific calculators, specifically the Texas Instruments TI-89 Titanium Edition Scientific Graphing Calculator, displays engineering format and how a user enters and interprets these values. This lecture is meant to be a follow-along exercise. As such, go get yourself a TI-89. Don't worry, I'll wait right here until you return. Since this might be your first exposure to the TI-89, let's do a quick walkthrough. The TI-89 is the metaphorical sword with which you will fight many battles the next couple months, and it will help you immeasurably if you know how to slash, stab, and at the very least, differentiate between the blade and the grip before you rush into battle. This being said, the calculator is not a magic sword, and it will not tell you what to do nor how to apply the concepts we've discussed. You're the one that makes the decisions, and the calculator just does what you tell it to do. Never forget this fact. The moment you trust a machine is the moment you lose. Never trust these devious little devils and always treat as suspect their results until you've judiciously inspected them and determined if the results make sense. The simple act of fat fingering a wrong key in a rush will most likely yield meaningless results. Results should behave within the bounds predicted by theory. Let's start with a brief orientation of the TI-89. Obviously, there's a display and a keypad. The row of buttons immediately below the display are function buttons 1 through 5. These buttons take on different roles depending on the mode you're in. There are some arrow key navigators in the upper right, and the enter key is in the lower right. You'll notice each key has more than one number, letter, symbol, or function written on it. The symbol written on the key is the natural function of that keypad, meaning if I haven't pressed any modifiers, the 7 key will output a 7. If, however, I press a modifier key like the alpha key, the 7 key will write the letter G, as indicated in the upper right-hand corner. If, however, I press a light blue second key modifier, the 7 key will write the squiggly worm symbol used for integrals, again as indicated next to the key in light blue. In summary, most keys have more than one option: the unmodified, the second, and the alpha option. I should also point out that the negation sign key at the bottom is different than the subtraction operation key. To negate a number, press the negative sign and the number of interest. We'll examine calculator operations beyond engineering format in later lectures. The single most important key on the TI-89 is the mode key. This accesses 3 basic setup screens accessible via the F1, F2, and F3 keys below the main screen. If someone tosses you a TI-89 brand new out of the box, or yours straight up dies in the middle of an exam, true story, you should be able to set it up in 30 seconds or less and be ready to rock and roll. This is equivalent of being able to field strip, repair, and reassemble a firearm in a combat situation. The TI-89 won't work well if it's in the wrong mode, and you need to be able to get it in the right mode as quick as possible. The first screen has 8 options which you can choose from. We're going to deal with 4 of them, principally display digits, angle, exponential format, that's kind of the topic of today's lecture, and complex format. Walk down to display digits using the down arrow and then press the right arrow key to access the menu. There should be a list going from 1 to Q. Walk down the list with the down arrow key. The option I'm going to choose is E, float. Not float 1 or float 12, straight up float. Option E, between D, fix 12, and F, float 1. Press enter to save this option. Walk down to the angle entry using the down arrow key and press the right arrow key to access the menu. Walk down the list with the down arrow key. The option I'm going to choose is 2 degrees. Press enter to save this option. Walk down to exponential format using the down arrow key and press the right arrow key to access this menu. Walk down the list with the down arrow key. The option I'm going to choose is 3, engineering. Press enter to save this option. This is the option we're going to spend some time discussing today. Finally, on the F1 page, walk down to complex format using the down arrow key and press the right arrow key to access the menu. Walk down the list with the down arrow key. The option I'm going to choose is 3, polar. Press enter to save this option. What did we just do? Regarding the angle and complex format, don't worry about it. These are settings that we'll use in later lectures on introductory AC circuit analysis. The angle measurement sets up to measure distances around a circle in useful degrees, as opposed to useless radians. The complex format sets up to display a vector in polar format with a magnitude and angular direction, as opposed to rectangular format with vectors in both the real and imaginary axis. The display digits you'd think is kind of a matter of personal preference, but it isn't. I want you to put it in float because it allows you to make the decision which place you want to round a value to. If your instructor tells you to round something to the tens place, round it to the tens place. If you have available all the digits, as the float option allows, you'll have accessible all the dirty details to the right of the decimal point and call or keep as desired. We'll examine rounding in later lectures. We'll return to discuss engineering format in a moment. Let's move on to the second page of the mode function by pressing F2. You can pretty much ignore everything on the F2 page with the exception of the last 2 options, exact versus approximate and base. Walk down to exact versus approximate using the down arrow key. Press the right arrow to open up the menu options. Use the down arrow key to walk to option 3, approximate. Press enter to select this option. The base we're going to be using is decimal. All of humanity uses the decimal or base 10 system. 10 digits, 10 fingers. A coincidence? I think not. If you want to dork out and talk to your computer, you can switch it to binary or hexadecimal mode. We'll learn about binary, hexadecimal, and related packaging of numbers used by people trapped in the 1980s, octal, and later lectures on digital electronics. What's the significance of exact versus approximate? I'll explain in greater detail in later lectures, but it has to do with how the calculator displays irrational numbers and repeated decimals. Think of the expression 1 divided by 3. The exact value of 1 divided by 3, believe it or not, is the fraction 1/3. It can't get more exact than that. However, fractions are extremely unbecoming in the engineering world, and we need to represent this answer as an approximated decimal form. The approximation of 1/3 in decimal form is 0.333333, and so on into infinity. This is where the display digits float comes in handy. Round to the nearest tenths place, 1/3 is approximately 0.3. Round to the nearest hundredths place, 1/3 is approximately 0.33, and so on. All right, that's all we really need to do in mode. Let's get out of here by pressing enter to save our choices. In summary, display digits float, angle, degree, exponential format engineering. This is the topic we're going to be discussing today. Complex format polar. On the second page, exact versus approximate must be an approximate, and base must be in decimal. Let's now return to our intended topic, engineering format as displayed on the TI-89. We've got 2 tasks. 1, learn to read a number displayed in engineering format in the TI-89, and 2, learn to enter a number using engineering prefixes into the TI-89. Here's the key to interpreting numbers as displayed on the TI-89 in exponential format engineering. It's got 3 parts. The TI-89 displays a coefficient next to a capital E next to a power 10. This is the calculator's way of saying take the coefficient and multiply it by 10 raised to that power. If the calculator is displaying 2e3, it means take the coefficient of 2 and multiply by 10 raised to the third power, where 10 to the third power is 1,000. 2 times 1,000 is 2,000. If this number represented a quantity of power, units of watts, this would be 2,000 watts. Or using engineering prefixes, 2 kilowatts. Here are 3 totally wrong interpretations of engineering format. First, 2e3 does not mean 2 raised to the third power. 2e3 means 2 times 10 to the third, or 2 times 1,000, or 2,000 watts, or using engineering prefixes, 2 kilowatts. Second, 2e3 does not mean 2 times e, notice the lowercase e, raised to the third power. Lowercase e is an important mathematical constant serving as the basis of the natural logarithm. Numbers like e and its irrational BFF, pi, are transcendental and play an important recurring roles in mathematics. As cool as this is not what engineering format means. 2e3 means 2 times 10 to the third, or 2 times 1,000, or 2,000 watts, or using engineering prefixes, 2 kilowatts. Finally, 2e3 means absolutely nothing to the outside world. Only in TI-89 calculator land does this mean anything. If 2e3 represented a quantity of power in units of watts, and you were to enter 2e3 on an exam, you get the answer to that question wrong. 2e3 means nothing. It's just a method your calculator uses to display numbers in engineering format. Again, 2e3 means 2 times 10 to the third, or 2 times 1,000, or 2,000 watts, or using engineering prefixes, 2 kilowatts. All 3 of these interpretations are wrong. There is one and only one proper interpretation. The TI-89 tells us the coefficient, in this case 2, tells us we're in engineering format with a capital E, and to what power of 10 we're multiplying the coefficient by. In this case, 10 to the third or 1,000. We know the engineering prefix associated with 10 to the third or 1,000 is a kilo or small k, so if this is a measure of power in units of watts, the calculator is saying 2 kilowatts. Can you dig? Here's a couple more examples. Let's say the calculator is displaying 3.5 e negative 3. Let's pretend this is in units of amps. The TI-89 tells us the coefficient, in this case 3.5, tells us we're in engineering format with a capital E, and tells what power of 10 we're multiplying the coefficient by. In this case, 10 to the negative 3, or 0.001. We know the engineering prefix associated with 10 to the negative third, or 0.001 is a milli, or small m. So if this is a measure of current in units of amps, the calculator is saying 3.5 milliamps, where 3.5 milliamps is equivalent to 0.0035 amps in the base unit. Let's say the calculator is now displaying 1.72 E6. Let's pretend this is in unit of ohms. TI-89 tells us the coefficient, in this case 1.72, tells us we're in engineering format with a capital E, and what power of 10 we're multiplying the coefficient by. In this case, 10 to the 6, or a million. We know the engineering prefix associated with 10 to the 6 or a million is a mega or capital M, so if this was a measure of resistance in unit of ohms, the calculator is saying 1.72 mega ohms, or 1.72 mega ohms, is equivalent to 1,720,000 ohms in the base unit. Got it? Your turn. Given this batch of numbers as displayed on a TI-89 and their associated units, see if you can interpret the number in both base units and proper engineering format. Again, both base units and proper engineering format. By all means, pause the lecture and try this yourself. If you're tracking, you should have obtained the following values. 47e negative 6 means take 47 and multiply by 10 raised to the negative 6, or 0.000001, which is 0.000047. If you're using engineering prefixes to represent this quantity, I could say this is 47 microfarads. 3.9E3 means take 3.9 and multiply it by 10 raised to the third, or 1,000. 3.9 times 1,000 is 3,900. The engineering prefix associated with 10 raised to the power of 3 is a kilo, so I could say this is 3.9 kiloohms. 70E negative 3 means take 70 and multiply it times 10 to the negative third, or 0.070 amps. The engineering prefix associated with 10 to the negative third is a milli, so it's more appropriately expressed as 70 milliamps. 680E0 means take 680 and multiply it by 10 raised to the 0, where 10 raised to the 0 is 1. Anything raised to the 0 power is 1. 680 times 1 is 680 ohms. Given we're already at the base unit of ohms, the engineering prefix is unnecessary, and this would most naturally be written as 680 ohms. Our next entry, 22E negative 9, means take the coefficient 22 times 10 to the negative ninth. In the base unit of farads, this represents a quantity of 0.000000022 farads, more appropriately expressed in engineering format as 22 nanofarads. The next entry, 2.3E6, means take 2.3 and multiply by 10 raised to the 6, or million, or 2.3 million watts. The engineering prefix associated with the power of 10 to the 6 is a mega, so this is more appropriately expressed as 2.3 megawatts. Lastly, 1.15E9 means take the coefficient 1.15 times 10 raised to the ninth. So this is more appropriately expressed as 1.15 gigawatt hours. If we restricted ourselves to the base unit of watt hours, it'd be 1,150,000,000 watt hours. Okay, that wasn't too hard, was it? You should be well versed in reading numbers as displayed on the TI-89 using engineering format, where again it's 3 parts: a coefficient, an E, and a power of 10. Now, let's stand this concept on its head, and rather than reading numbers, let's learn to enter numbers into the calculator using the engineering format. You'll be happy to know that entering numbers in engineering format is just as easy as finding a sketchy neighborhood in Detroit. You can't not enter a number in engineering format when the TI-89 is in engineering mode. That's the point of having an engineering mode. It takes any confusing pile of numbers you enter, chops it up, and displays it in an easily readable manner. As long as you're entering the right number, you can enter this number in any fashion you see fit, and the calculator will immediately recognize to what power of 10 it needs to raise to make it the most readable. For example, consider the number 68 kiloohms. This is 68 times 10 to the third, or 68 times 1,000, or 68,000 ohms. I can enter 68,000 into my calculator by entering 6, 8, 3 zeros and follow it up with an enter key. The calculator returns 68E3, meaning it has gone to the trouble of converting it to engineering format using its own peculiar display method. This method works, but entering long strings of zeros is a serious pain, so often enter them using shortcuts using the power of 10 or EE key. If I enter 68EE3, the calculator recognizes that I want to multiply 68 times 10 raised to the third power, or 1,000. Press enter. This also yields 68E3. How easy is that? But wait, there's more. Even if you enter the number in some weird alternate fashion, let's say scientific notation, the calculator will do the conversion to engineering format for you. 68,000 in scientific notation is 6.8 times 10 raised to the fourth. If I enter 6.8EE4, the calculator still spits back 68E3. As long as your calculator is set up in exponential format engineering using the mode key, you will never have to worry about this again. The calculator puts any number you enter into engineering format. Consider the following selection of numbers. By all means, pause the lecture and punch these numbers into your calculator using whatever method you wish and press enter. If you're in exponential format engineering, you should get the following results. 6.75 megawatts could be represented as 6.75 times 10 to the 6, or 6,750,000. If you wanted to, you could enter 6, 7, 5, 4 zeros and press enter. The calculator would return 6.75E6. Although effective, this is inefficient. Go straight into engineering format. 6.75 megawatts is 6.75 times 10 raised to the 6. Enter this as 6.75 EE6. Again, the calculator returns 6.75 E6. Same results with less keystrokes. That's the point of engineering notation. It makes unusually large and unusually small numbers less cumbersome and easier to manipulate. 33 microfarads could be represented as 33 times 10 to the negative 6, where 10 to the negative 6 is 0.000001. If you wanted to, you could enter decimal point, 4 zeros, 33, and press enter, and the calculator would return 33 E negative 6. Again, this seems super inefficient. Enter it in engineering format. 33 microfarads is 33 times 10 raised to the negative 6. Enter this as 33 EE negative 6. Again, the calculator returns 33 E negative 6. Same results, only faster. Just for the heck of it, let's enter 4,500,000 hertz in long form. 4-5 followed by a shit ton of zeros. 4,500,000 hertz is 4.5 times a million, or 4.5 megahertz. Alternatively, we could have entered this as 4.5 EE6. Either method of entry results in 4.5 E6 being displayed on the calculator. Finally, 2.56 times 10 to the negative 7th is a number expressed in scientific notation. For those with some experience in scientific notation, you'll realize 10 to the negative 7 is a shift 7 decimal places, meaning this number is 0.000000256 when expressed in the base units of grams. You can go to the trouble of learning scientific notation and laboriously enter it as 0.000000256. However, we are not training to be scientists. We're training to be engineers and technicians. Not only do we get paid better than scientists, we're better looking, and we use engineering notation to get the job done. It's far faster to enter it directly in the format you've been given as 2.56 EE negative 7, and that calculator takes the junky scientific format and properly reformats it, as would a good-looking, high-paid engineering technician, as 256 E negative 9, or using engineering prefixes, 256 nanograms. Thank you, calculator. Your work here is done. Last quick note before we go. While in exponential format engineering, the TI-89 will display all fractions in engineering format. For example, 1/2 is 0.5. The TI-89 will display 0.5 as 500 E negative 3, which means 500 times 10 to the negative 3rd, or 0.5. Similarly, 1/4 is 0.25. The TI-89 will display 0.25 as 250 E negative 3, or 250 times 10 to the negative 3rd, or 0.25. Those unfamiliar with engineering format might be a little taken back by this at first, but it makes sense. While in exponential format engineering, the TI-89 displays every number you throw at it in engineering format. That's it. This concludes this short introduction to engineering notation as implemented on the TI-89. We'll be making use of these skills all day, every day, for the rest of your life, so get good at it now. If you're less than confident with your ability to write and read engineering notation on the TI-89, I'm asking you to get confident in these skills before moving on to the next topic. By all means, rewind and revisit this lecture as many times as you need. Practice, practice, practice. Engineering notation and the scientific calculator may be entirely foreign to you, but trust me, just like learning a new language, it'll get easier and more natural with repeated exposure. In conclusion, this lecture took a look at engineering notation as implemented on the TI-89. We learned to set up our calculator using the mode key and place it in engineering format. Then we learned to interpret and enter numbers in engineering format. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.